The following is my talk at the Magnetic Recording Conference, which was in August 2021 and was held virtually. In this presentation, for the first time, I have mentioned about the second mechanism of parametric magnetization reversal by means of Cant modulation of anisotropy field. In this case, same as for mechanism 1, Cant induced spin accumulation due to Hall effect, and which affect anisotropy field. Also, I would like to apologize that in the talk several times I use terms paramagnetic but instead of parametric. It is always parametric. Hello everybody, my name is Vadim Zayats, and today I will talk about the paramagnetic mechanism of magnetization reversal in nanomagnet. It can be used as an effective low-energy recording mechanism for MRAM. The parametric magnetization reversal occurs when some magnetic parameter of nanomagnet is modulated with resonance with magnetization precession. As a result, even small modulation reverses the magnetization direction. As example is shown, when a weak magnetic field SCO is applied perpendicular to the magnetic z-axis, a weak magnetic field only slightly tilts the magnetization from its equilibrium direction without any chance of magnetization reversal. However, in case when the external field is modulated so its phase and frequency are matched to the magnetization oscillation, even a tiny field reverses the magnetization. That is the main idea. In this presentation, I would like to compare the effectiveness of two mechanisms of parametric reversal. There are two types of paramagnetic reversal which are common for any mechanism of paramagnetic magnetization reversal. The first type is by RF modulated current or RF modulated external magnetic field. This mechanism is relatively simple. For example, when external magnetic field is modulated at frequency close to the FMR frequency, and there is a resonance increase of precession angle. The second type is by DC current, when none of external parameters are modulated at RF frequency. In this case, the DC current amplifies a random thermal fluctuation of correct phase and frequency. The parametric mechanisms are distinguished by the magnetic parameter of nanomagnet, which is modulated by RF current. Today I will compare two mechanisms which are both induced by a spin accumulation, but direction of accumulated spins are different. For the first mechanism, the spin direction is perpendicular to the magnetization direction. As a result, the magnetization is tilted due to the magnetic field induced by the spin accumulation. For the second mechanism, the direction of spin accumulation is along the magnetization, and therefore the magnetization direction does not change. However, the spin accumulation affects anisotropy field, which is used for the parametric resonance. Main benefit of parametric magnetization reversal is a small required recording energy. For operational MRAMs, there should be substantial an energy barrier between spin down and spin up state. Otherwise, the magnetization can be reversed by thermal fluctuation. In cases of conventional 2 or 3 terminal MRAM, the magnetization reversal is based on continuous spin injection. During the whole time of magnetization precession and reversal, the spin injection should provide the energy larger than the barrier. In contrast, for parametric reversal, the required energy is much smaller. Due to its resonance nature, the energy barrier is climbed up by tiny steps like this. Next, I discuss the first parametric mechanism, when the spin directions of the spin accumulation is perpendicular to the magnetization, and magnetic field induced by the spin polarization tilts the magnetization. The important feature is that the magnetic field and therefore the magnetization tilt are proportional to the electrical current. The paramagnetic resonance occurs because of this feature. This slide explains how to measure magnetic field which is induced by spin accumulations. There are two methods. The low precision method, which is called the method of second harmonic, and in which the current is modulated at low frequency of about 1 kHz, and second harmonic of whole voltage is measured. The magnetic field of spin accumulation tilts the magnetization. As a result, magnetization direction is modulated. The whole voltage is proportional to both the current and magnetization. Since the both are modulated, the frequency beating creates the second harmonic. The second high precision method measures the whole voltage at DC current. While the external magnetic field is scanned, the magnetic field which is induced by spin accumulation shifts the measurement data, and from the symmetry of the data the field is evaluated. This slide shows the measured result. The magnetic field which is induced by spin accumulation depends on electrical current and on external field which is applied perpendicularly to the plane. Both dependencies are clearly related. This is interesting physics explaining this. However, I like to emphasize that measured magnetic field is only 20 stat. The field is too small to noticeably affect the nanomagnet. However, if the field excites the paramagnetic resonance, it has a huge influence on nanomagnet. This slide shows the specifics of parametric resonance. Features of parametric resonance are rather unique for magnetic system. As you can see, there is a magnetization precession around the axis whose angle constantly increases and sweeps between the left and right. When the oscillation of the field is in phase with magnetization precession, each period the precession angle increases per angle for phi. The phi small angle of about 100 milli-degree as estimated from measurement of previous slide. This slide shows the calculations done for the parametric resonance. The Landau-Lifshitz equations were analytically solved with oscillating field. This is the solution, which is depicted on this graph. The graph shows torque versus time when there is a frequency mismatch. Even initially the paramagnetic torque is very strong. It's quickly decay in time. Additionally, at any time moment, the pumping torque must be larger than the damping torque. The damping torque was calculated from Landau-Lifshitz equations here, and from mechanism of photon or magnon emission shown here, and calculations here. In both cases, the torque depends on precession angle. It makes additional mismatch for paramagnetic resonance. From this slide, I would like to emphasize a major challenge and problem of paramagnetic resonance, a necessity of constant frequency and phase matching. This slide explains the mechanism of paramagnetic magnetization reversal by a constant DC electrical current. Such reversal is possible only because of positive feedback loop. The larger SCO field make angle of magnetization precession larger due to paramagnetic resonance. The larger precession makes larger modulation of electrical current due to magnetoresistance effect. The larger modulation of current makes an even larger modulation of its STO field. It is not only that the positive loop enhances a thermal magnetization precession until the magnetization reversal, it solves the problem of the phase and frequency matching for parametric resonance. This slide shows the details of positive feedback loop for a tunnel magnetic junction. Magnetization oscillations create the resistance oscillations, which create current oscillations. Since STO field is proportional to the current, STO become modulated and the magnetization precession become even larger due to the parametric resonance, and so on and on and on. This slide shows a second mechanism of parametric reversal due to current modulation as an anisotropy field. In this case, the spin of spin-accumulated electrons is directed up along the magnetization. The magnetization is not tilted due to the spin accumulation, but the anisotropy field of the nanomagnet is changed instead. This slide shows a measurement of current-induced change of anisotropy field in iron cobalt boron nanomagnet. This is measurement set up when in plane external magnetic field is scanned, the magnetization is tilted. The in-plane component of magnetization depends linearly on the in-plane field. From the slope of the measurement dependence, the anisotropy field is evaluated. The slope clearly depends on current. This is measurement data as a function of additionally applied external perpendicular magnetic field. The dependence of an electrical current is substantial. The change of anisotropy field is of about 100 step. This slide explains the importance of a bias in plane magnetic field for this mechanism. In absence of external field, the modulation of anisotropy does not affect magnetization at all. In contrast, an in-plane field tilts the magnetization, and the tilted angle depends on the anisotropy field, and therefore changes when the anisotropy field is modulated. This is conclusion.